Fantastic. So thank you everyone for joining us. My name is Ollie Robbins. I'm the outgoing YPN rep for the Southeast Area Committee. The presentation you're about to see, I wish I could claim credit for it, but it's all Colin's hard work. So the idea of this session is that Colin's going to give you a relatively high level overview of pumping applications and pumping technology. So hopefully anyone, regardless of your prior experience in this area, can get into this. And the idea is that we then begin to set up some future deep dives into any areas that you find particularly interesting. So as we go through, please do keep in mind any areas you'd like to know more about. And when Colin concludes, probably at the 45-minute mark, I reckon, Colin, we'll then open
Okay,
up for
yeah.
discussion. We can pick up any questions and also pick up anything that you'd like to see next. If you do have urgent sort of clarification questions as we go through, just stick them in the chat, and I'll do my best to verbalise those without disturbing Colin's flow too much. So over to you, Colin.
Thank you very much for the introduction. Good morning, everybody. As you've probably seen, I'm a older gentleman who spent many years in pumps, and this is just an overview and a start. So if any of you, as Ollie said, want to take it further, then we're happy to look at developing that sort of thing for you. I have to say, I did this presentation first a good few years ago. So any pumps you see are just generic pumps, just ignore any names or think of styles, because currently I work for a company and you can see in the background. Feel free to put questions in and feel free to give feedback on what you think. With that, Ollie, are you okay if I share my screen and
Go for
bring
it,
up the
Colin.
presentation? And let me know if it's shared successfully.
It's come up successfully for me. Are you going to put it into presentation mode?
I'm just about to.
There we go.
So
Success.
perfect. So the part played by pumps, an insider's guide. And that picture is one of a pump. And you think, what are pumps? Where are pumps? Pumps are everywhere. People say the horses brought us out the dark ages or the canals or things like that. No, it's pumps. It's pumps that move the water, move the sewage, move the chemicals, create the body products, even some of the foodstuffs. So there is so many things. And a pump forms part of what we call a system because you've got a pump, the pump moves, and I'm going to say liquid, and I'm going to use the term liquid very loosely because the pump is part of a flow system. The pump moves the liquid, but you want to move that liquid from somewhere. We call that the suction side. It's where you're going to pull the liquid from, whether it's, a pump just dropped into a swimming pool or whatever, it's going to pull that liquid through. So that's called the suction side. And on that suction side, you have a source, you have connecting pipe work, and I've put there the phrase associated equipment. You'll have come across pressure gauges, temperature gauges, you can have flow meters, you can have things injecting liquid into the pump, and then it goes into the pump. The pump then moves it to what we call the discharge side. And again, you get the associated equipment, the connecting pipe work to the discharge point. Now, the key thing of this, the key takeaway is you have a pump in the system, but there's a source where you need the liquid to come from and a discharge point where you want the liquid to go. And you get sort of the pump geeks like me that say, right, this pump goes there, can do this, can do that. But look at it as a whole system, not just the pump, because the system has an impact on which pump technology and what you're trying to do. But the key to the flow system is the pump. So we look at a flow system and we've got two parts. We've got what we call fluid dynamics and best pump technology. Now, fluid dynamics are about the liquid, what you're trying to move, what you're trying to pump. What is the liquid or the media? The flow rate is the rate at which you want it to move. The suction and the discharge are those two parts I've just explained. And then what do you need? Do you need accuracy? Do you need repeatability? Do you need hygiene? And you use those, dependent on the liquids. If everyone thinks it's pump to pump water, it's fairly easy. You get a flow rate, pressure head, which is the discharge pressure of the pump, and it's nice and easy. But say you're pumping, I don't know, sausage filling, say you're pumping body cream, suddenly everything changes, and it might be different technologies and different ways of doing it. Say you're pumping an oil. So the fluid dynamics are a very critical part of what you're trying to do, to think of what pump technology you need, and you need to make it work. So you've always got to think of the fluid dynamics. And once you've thought of the fluid dynamics, you want to think of the best pump technology. Now, I've put cost of ownership here because cost of ownership, if you're only going to use the pump once every couple of years, you just want a cheap and cheerful pump. If it's a pump that's going to be running on all the time, you want something with a very efficient system and an efficient motor. Then the area and the environment it's in. Again, another critical thing, because is it outside? Is it inside? Is it inside in a hygienic environment? Is it an explosive environment? I've pumped some very strange things over the years. Maintenance. Is it easy to get to? Do you need to do maintenance? You don't want a pump that requires high maintenance, that you've got to have a confined spaces requirement to get down to, because it's hard work. And then I put hygienic, but there's hygienic, there's high temperature, there's high pressure. There's a lot of considerations to pick the best pump technology. And these are all important considerations for the flow system. And then once you've got the flow system, it all comes down to the pump. So from that point, I'm going to talk to you about some pump technologies. I've got 6, 7, 8 pump technologies we can run through. Now, these are generic pictures of the pump technologies. And the most common one you'll come across is the one on the bottom left, is centrifugal pumps. Now, centrifugal pumps, very much within the water industry, within the wastewater industry, many areas like that. So a centrifugal pump, what is a centrifugal pump? These are just a couple of pictures of them, but they go much bigger. They are accounting for 70%. So 70% of the pumps out there are centrifugal pumps, but they mount them in different ways. They can be vertical, they can be horizontal, they have different impellers. But our life today wouldn't exist without these pumps. They're good for continuous duty. They are what we call a pulseless flow. So when you turn the kitchen tap on and the water comes out as a straight stream, that's a pulseless flow. And they can do very high flow rates. There's pumps that are bigger than me. I can sit at a table on a desk, sorry, a desk on a chair inside the pump casing. They're that big. The secret is how they work. So this is what we call an end suction centrifugal pump. So this is just one example. If you look at it, there's a red bit in the center, which is called the impeller. This is, some refer to as the spinny bit. So the impeller is where the liquid goes. The liquid goes in what we call the suction side, although it doesn't do a true suction lift, it needs liquid there to go in. The liquid goes into the impeller, and then the impeller has vanes. If you look to the drawing on the right, these large vanes, and the liquid, the impeller turns one direction, accelerating the liquid up these vanes into, and it's specifically shaped, a volute casing. So you see the volute casing, the blue line, that allows to then accelerate the liquid further to the discharge point, what's called the pressure side, and exit the pump. This is a rotational pump. This is smooth flow. But the way this impeller works, and there is many different types of impellers for abrasives, for solids, for soft solids, for hard solids, all sorts of things. We have recess, but they all fundamentally work in the same way, which is take the liquid and you see these particles spinning, send it, accelerate it round that volute casing and out. And that is essentially how a centrifugal pump works. If we think centrifugal, why? As I said, they're very efficient. They have a very good working life, and you can fit them with IEC3 motors and things. So they give you a payback in that respect. In terms of the flow rate they can move, they don't take up a big footprint compared to some other technologies, and they're pulseless. They do have limitations. They need liquid. They can't run dry. So run dry is running the pump without any liquid in it. They need liquid to run. We can adjust the flow rate slightly because we can fit what we call a VFD, a variable frequency drive, but there are limited control in adjusting the flow rate. And extreme abrasives and things, there is issues. Pardon me. But they are 70%. They are widely used by the water authorities. They pump all the clean water and stuff like that in different formats, and then all the dirty water. They basically, most of the things you use in life, from paint coatings to body products to hair products to a lot of foodstuffs, are used. These pumps are used within their production. That's my little bit on centrifugals. I'm going at pace, I'm afraid, because it is quite a lot to get through in the timescale. The next one I'm going to talk about is a diaphragm pump. Some call it the flappy pump, because a diaphragm is a very basic pump. It has a minimal number of components in touch with the liquid. It is a true self-priming pump because it can pull liquid into itself, but only a limited amount. Within the industry, we define self-priming as just being able to pull liquid in. Some pumps can self-prime a lot more than others. But also, because a diaphragm is a very specific area that's moving, it's a very controllable flow rate. Because a diaphragm pump, as you can see from this drawing or animated drawing, has a suction side where the liquid comes in and a discharge side where the liquid goes out. On the suction side, that's showing a ball valve. Can also be another thing called a flap valve, but it's a ball valve. As the diaphragm pulls back and fills the chamber with orange liquid, it is lifting the ball at the bottom, the ball valve, and pulling the liquid in. It's also pulling the discharge valve at the top down, so sealing off that hole to ensure that it fills with liquid. And then as the diaphragm moves forwards, to empty the chamber, it's pushing the liquid out the top through past that ball and pushing the bottom ball into its hole to seal it and hold it there. It's not a complicated pump. It might be better explained by this drawing, which shows the pump has filled in section 1, and you can see it's used something mechanical to pull the bar back and fill the chamber. And it then goes on to its what we call the discharge stroke. So it pushes this forwards, starts to empty the pump chamber, pushes the bottom ball into its hole to seal that valve. That's known as a ball valve. And pushes the liquid out the top, which is drawing number 3. And then you get to drawing number 4, which is the chamber is emptied. It's, again, not complicated. But we have to think again, where would you use this pump as opposed to a centrifugal pump? And these pumps can run on electric or air. Air is quite a favoured drive medium for them, so you have an air motor in there. And you look at the strengths, the applications, the limitations. they come in a variety of materials, and because of the nature of them, they can make them in plastics and some very chemically resistant plastics. They even go as far as, I know some companies do them in PTFE, which is one of the most resistant plastics we have. They're very good at going at a steady, repeatable flow. And the reason maintenance, because they're not a complicated pump. It's a very easy pump to strip and repair. There's not some of the finer assessments and adjustments you have on others. They don't like abrasives, because if you think of those balls that are in the ball valves, if there's an abrasive flowing past that, it will wear the ball and stop the ball sealing. The ball will eventually, I've seen it where they come through that hole. They're very good for chemical. They're used a lot within the food industry as well, but they tend to try and use metal casings rather than plastic casings. And then you can go down to this picture here is a very small one, so they're very good at small dosing. So I don't know, you may have seen them if you've been on to some of the treatment works and things like that, used in the dosing capacity as a small version. That's essentially the diaphragm pump flying through these. The next one I'm going to go to is called a gear pump. And the gear pump, this is just a couple of examples, can be very small, what we call a micro gear pump, can then come to a slightly larger version of a gear pump, and they can get bigger still. The thing with the gear pump, it's another spinny pump, it's very, very accurate and it's pulseless, but it can also achieve high pressure. So anywhere you're doing hydraulics, anywhere, they're used a lot on diggers and things like that for the hydraulics to lift the arms and things. Their operation isn't complicated. Again, one little picture for you. Liquid in. Liquid goes round the outside of the gears. So it's called a gear pump because it's two gears working together. One is a driving gear and one is a driven gear. And you have very key points. They have to seal against the outside of the chamber, and then they have to seal against themselves as they're put together. Now, these gears can be made of plastic for chemical resistance or metal, dependent on what you're trying to do. But the sealing of the gears against themselves and the gears against the outside is critical, because if you don't have those sealing points, i.e. the tips wear, then you'll get backflow. The V of the gears is called sort of the pump chamber, if you will, the gear valley. And it's just the faster you spin the gears, the more liquid you push through it. So again, it's not a complicated technology as such, but having the understanding of what a gear pump is does help you understand what it's going to do. It's very good on things like oils and things like that, but you don't want to pump body cream because you would chop it up. So that's why they're very strong within the hydraulic industry, but they're also very accurate for small dosing. You have the gear valley I was talking about. You have the mesh point I was talking about, and you have the top one is the driving gear and the bottom one is the driven gear. That's done by a cog behind, not gear to gear like that. And then you look at gear pumps and it's back to another why. Good working life, but it's the accuracy and the medium viscosities. I've said the oils, we've said the hydraulics. They can't run dry, because if they run dry, the tips will heat up. Where there's the contact, you get friction creates heat, and that causes damage. But they are very accurate and they can go for very high pressures. And as I'm talking, please feel free to put questions into the chat or the notes as we're going through this. The next one I'm going to talk about is peristaltic. So what is peristaltic? And I go, how many pumps do we have in the human body? People go, oh, the heart's a pump. Oh, yes, the heart. It's almost the diaphragm pump. But there's also a peristaltic pump, which is the esophagus. because that's a tube that squeezes, moves, and releases. And a peristaltic pump is basically a tube. It's going to squeeze and take in a pocket of liquid. This is done by rollers. If you look at this bottom left-hand drawing, which then come on, and you go to the middle drawing, a pocket of liquid, but the rollers are turning, so they're moving that liquid along the tube. The tube isn't moving, they're moving it along the tube. And then they push it out the tube at the other end. And then as the next roller comes on, it's bringing up the next slug of liquid, as you would. And so it's doing it with a tube. Now, we use the term tube because a tube is an extruded plastic tube, so they go very small and very fine. But they also make what they call hose pumps, where they have a much bigger hose because it needs reinforcing. So these can actually go up to 4-inch, 6-inch. They make very large versions. And again, there's very specific applications for them. They're very strong within the pharmaceutical biotech type market. They are very good for pumping things like live cells because they don't damage it. They grab slugs or pockets of it, and as the roller comes onto the tube, it pushes the liquid forwards and backwards. So it's not really trapping anything in the gap between. Hence, the bio industry is very strong with these. The peristaltic strengths, I said, they're good flow ranges. They're not bad. They're not the biggest, but they're not bad. But the liquid is contained within the tubing. It's very easy to keep it hygienic because you have a tubing that you can autoclave and then you put in the pump, and it's very hygienic. And their dosing and dispensing is their key things. They're very much handling what the other pumps can't. The tubing is a consumable, like the car tyres, and the flow rate and pressure is limited by the size of the tubing. But it's also very, very accurate. It's not the most accurate pump, but can be very, very accurate. The next one, piston pump. So piston what? And different types. Again, shown there, micro piston, and then a large version of a piston pump. It's very basic. You know, people say you've got pistons on your car if you've got an old school car. And you do have pistons, and they move through a very specific area. That's why they're called positive displacement pumps, with some of the others like the diaphragm pumps and things like that. So a piston pump moves a very specific amount of liquid at a time, and it allows control over that liquid. And also, because you're moving a piston in a bore, you can achieve high pressure. It works by moving a piston, the blue bit, backwards and forwards in what we call a pump chamber. The ball or sealing arrangement, very, very similar to the diaphragm pumps we were talking about. And again, they can have flaps instead of the balls. But you have to have a seal across the side of the piston to stop the liquid leaking back. And then invariably an electric motor running a cam. It's got a suction valve on the suction side and a discharge valve on the discharge side. So you do need both valves to make it work. Otherwise, it would just warm the liquid up. And then there's actually a slightly more radical version, which is called a rotary piston pump. And this uses a motor directly onto the piston and brings it backwards and forwards as it turns. So it's not just using the piston side, it's turning at the same time to use that as the opening and closing of the piston pump. So your suction stroke has the little sort of bit one side letting, as it's going back, letting the liquid in. Then it turns round, and as that reaches the other side, it pushes down, it pushes the liquid out. But it allows, and these are only on a very small scale, very sort of micro side, very accurate control. But piston pumps can get very large. And a lot of the original pumps that were sort of Victorian designed were the piston type pumps. Just a sort of big thumping pump, I call it sometimes. And that's that technology. And you look at piston pumps and think, yes, They can achieve high pressures. They're very accurate and very repeatable. But that's why we talked in the beginning about what you need the pump to achieve for you, because in some ways they're greater wear rates and things. They can handle certain liquids but not others. They don't like particulates, because you're going to get issues with particulates going onto the seals and onto the valves. And they are what we call high shear. So if you move a liquid against itself, you're shearing it. If you put a lot of force into that liquid, you can also shear it. So if you're looking at what we call shear sensitive liquids, you can damage them. Things like some of the food products, things like some of the bio products, and it does have an impact on them. And then I go to progressive cavity. Sorry guys, this is flying through at pace just to try and sort of make it all make sense. But progressive cavity is a little more complicated. And again, you'll come across these. They're used, again, from the food industry to heavy industry. It's a more complicated pump, but it's a very, very useful pump. The only thing is, the bigger flow rate you need, the bigger the pump has to be. So they take up a rather large footprint. They're again called a positive displacement pump. So it has a very specific movement, which moves a very specific amount of liquid. But the way they work, they're what's called low shear and high viscosities. Imagine a piston. So you've got a pump chamber with a piston, because we've just talked about the piston pumps. Now imagine several pistons behind each other. And now make the wall thickness of those pistons 0. So they're all pushing at once, but 0. You end up with an arrangement like this, because what they do, it's actually what we call a worm drive turning within a rubber chamber. So it's a continual set of pistons going, because it's sealing off to the rubber chamber. It's an endless sort of piston PC pump. So you'll have the inlet and the liquid flows up. The liquid, by the way, is the blue liquid with the orange spots, and it flows like this. And it's continually going through. So they're very good with thick solutions, thick creams and things like that. Yes, there is a wear component. You know, the rotor is a stainless steel rotor. The rotor and the stator, the rubber bit, is normally rubber, so it does wear, but it's very effective at what it does.
Colin, we have a question from Heather in the chat.
Yep.
What's turn down ratio? Does this relate to pressure?
Turn down ratio. So turn down ratio doesn't relate to pressure. It's about slowing down the pump. So you would talk about a turn down ratio as being slowing your pump right down. What can you slow it down to? So if you're running one of these, a progressive cavity pump, and you wanted to reduce your flow rate to half, that's what you can achieve with your turn down ratio. Does that help at all, Heather? Give a thumbs up into the chat if that makes sense for you. I can happy to deal with the question and give more detail at a later date if you want.
Heather's happy with the answer. Thanks, Colin.
Brilliant. So progressive cavities, we said slurries and abrasives, because they're not putting much energy into the liquid, so they can cope with the abrasives because they've got the rubber stator. So they can cope with the abrasives, because if you've got rubber, if you're pushing something that's sort of water and sand, which is probably the most brutal solution at it, if it hits metal, it's going to abrade it quite hard. If it's hitting rubber, part of the energy in moving it is reflected back into the liquid, so it does less damage. They're used a lot within foodstuffs. I kind of don't want to frighten people, but you know, it's everything from mince pies to chocolate manufacturing and all sorts of things. You know, if you like chocolate, I've been to a facility where they're pushing around baths of chocolate and then use a pump to pump it into the manufacturing system. It's incredible to see. From that to what was it? The one that my wife laughed at was the Black Sea mud face packs, and that's all pumped and pumped into the packets and mixed up. It's incredible the world with pumps. Strengths of these pumps is they can pump the thicker liquids and the low shear, so they're good with the foodstuffs and things because they're not damaging the product as they pump it. If you use some of the other much faster spinning technologies, then it would shear or damage the product. You couldn't pump mincemeat with a centrifugal pump because it'll be fine slurry when it comes out, not the mincemeat product you want. And then, as I said, limitations. They do, if you want a high flow rate, you need a big pump. And it takes up a big, what we call a footprint, which is the area it takes on the ground. The biggest I've seen, they're like 5-6 meters long, but the flow rates aren't that great, but that's the size they have to be. And then there's quite a few moving parts. So there is quite a bit of maintenance required with these. And then we've got rotary lobe. Now this is very much, this little one here, very much hygienic, very much the food industry. And we talked about the gear pump, but the rotary lobe is similar but very different. The reason I say it's similar is it's got two rotating elements inside. It's very good for handling liquids containing solids. If you were pumping soup and things like that, and you didn't want to damage the product, they're very good for that. And they're very good for sanitary or hygiene because they're stainless steel invariably. So we have what we call CIP and SIP, which is clean in place and sterilize in place. Clean in place is where you put a cleaning liquid through it and flush it, essentially. And then sterilize in place normally involves pushing steam through it at a certain temperature to ensure that it's clean. But a lot of the food production facilities use this sort of pump. And it works, as I said, in a similar way to the gear pump. Your liquid comes in, but because it's called rotary lobe, because you've got a chamber again, as we were making the chamber in peristaltics, so we make a chamber here. So the liquid comes into the chamber, there's a little swift close off there, and it keeps it in the chamber till it pushes it out the other side. And again, you've got this sealing face here, but the liquid comes into the chamber and goes through, and just goes through. And the faster you spin them, the faster the liquid will go through. Again, when you strip the technology down of what the pump's doing, it's not complicated. It's all the other bits working around it to make it happen. And this is, as you can see, very good for the foodstuffs, for the thicker liquids. The strengths, the limitations, the applications, sanitary. It is very much sanitary. So all food and hygiene stuff has to have certain flanging things that can be cleaned. It's suitable for special cleaning processes. And it's good with slurries. It can't run dry, which is something we said. The ones that can run dry, and basically your diaphragm pump for a short period of time, the peristaltic pump for a longer period of time. And this is why, again, I go back to those 2 points at the beginning. You've got to think what you're trying to do with the pump and what you need to do with the pump. But they have a good life. They have a very long life. It's a more complicated service, but it does a vital role. And then the final one I've got to talk about, I'm just about doing okay on the time, I think, Ollie, is the syringe pump. So the syringe pump, you think, no, just used in hospitals, whatever. Very much in the biotech, very much for high accuracy. And when I say high accuracy, this is lifting it to the next level. This is talking flow rates of, so that look up there, that's picoliters. You couldn't imagine a picoliter. And then this high rate dispensing, you're talking dispensing accuracy of that 0.35%. repeatability of 0.05%. Most pumps are nowhere near that. And it's pulseless flow because it's pushing. It's essentially like the piston, but much smaller flow rates and very, very strong control. And the reason they use the very strong control is because when you come to it, it uses a thing called a stepper motor to just drive a little drive that pushes that bit, it's called plunger, pushes that into the syringe. And that's a little, that looks like a hospital syringe, it is. And you can see the drawing on the right shows your stepper motor, which is turning slowly and measuring how slowly it's turning through a gearbox. So it's a small wheel to a bigger wheel to achieve that flow rate you require. But this picoliter accuracy is essential, especially within the biotech world. And they can achieve what I call the push me pull you, because they can put a syringe the other way. So as it goes either way, it'll push one syringe and the other one will fill, and keep this very accurate flow. I doubt you'll probably come across these in what you're looking unless you're going into laboratories. But I once used them when I was recreating a reservoir dosing system on a micro scale for a company. And that micro scale was to ensure that the system was going to work. And then you look at Y syringe pumps, and it's, the big thing we said at the beginning, highly accurate. You can get higher pressures, we say up to 100 bar, because you can have metal syringes. You don't need to see what's in the syringe, so you can have metal syringes. Oh, it says there about the push me pull you. So you've got that push me pull you, and you can have multi-channels because you can have many syringes at a time going. But they are only for very low flow rates. But if you need that very low accurate flow rate, you can achieve it. I think I've pushed through this whole presentation at quite a pace. And it's very much, you've got to think efficient life costs. You've got to think the correct pump for the application, because these things go with reduced service need. Wait for the next one to come up now. And from water and many liquids in between. There's one more to come, to waste. There's a picture of everything. But if you look, you're sitting in front of a computer. Pumps were used in many different parts of manufacturing that computer. And if you've got a glass beside you, there's a coating on that glass. So pumps were used in doing that coating. If you've got a mobile phone, if you've got a cover, the walls painted around you. So much of what we do is impacted by the pumping industry and picking the correct pumps. Now, I've just gone through those technologies and just had a brief discussion on them. It's just a very basic because it's a 45-minute fly. But if there's specific ones you want more detail on, if you find it interesting, then please ask. And we can look, mention it to Ollie, put in the feedback, and we can look to develop some more. It's quite difficult sort of doing it just on Teams. I'm kind of getting a workout because my arms are moving all over the place as I explain things back here. But I love pumps. I'm quite sad because they do make a difference. And the foodstuffs, everything from burger meat to dog feed to there's just so many things I want to get to. I've pumped pharmaceuticals. It's just different things. Chemicals, it's different things, and chemicals used in different ways, whether it be water treatment or whether it be chemical process. And then water and wastewater. And I know, the issues with wastewater from fogs to raggy solids. And then that's covered by having different types of impellers that can shred material, impellers that can take the solids and make them smaller to push them as a slurry through the pump. To the paper industry, to the plastics industry. There is so much that this pumping technology is involved in our lives. I'm going to end my presentation there if it's all right, Ollie. I shall come out of that and stop sharing and then see if anyone's got any questions.
I've got to say, Colin, thank you so much for that. I've received this presentation a couple of times now, and I love the passion that you talk this through. And I think those animations really bring it to life as well. So thank you so much for that. We do have some questions in the chat, so I'll verbalise those now for you. A couple in the Q&A section from William. So firstly, I'm interested in pumps used at sampling taps. I'm never quite sure why the pumps are left in different conditions when not in use. Example, hand, auto, or off. What would be the benefits or risks associated with each?
So I missed the first part. I'm interested in pumps used.
At sampling taps.
Right. So if you've got hand, auto, or off, hand, I'm assuming is manual. Auto is going to be an auto function, then an off is no power. You'd be better just turning it off and not powering it. Auto may be if it's going to a specific sampling machine or something like that. Be interesting to see what sort of pump they're using. Just take a picture of it and send a picture by yourself or the institute to me, and I can have a look and we can have a bit more formative answer if you want.
Thanks, Colin. And second question from William. Some sample points become aerated and can give falsely high turbidity readings. What causes some pumps to give aerated water, but others pump water without issue?
Right. So watering the system depends, if you're talking centrifugal pumps, it depends on how they're mounted. Because and I've seen sometimes they mount submersible pumps in a slightly wrong direction, different orientation to try and achieve a reduction in the amount of pipe work, but then that can allow some air entrapment. And that air entrapment over time will feed into the system. And any time where the pipework kind of goes up and down, will sit there. As the water flows through, it'll pull a nominal amount of air with it. It'll clear the whole bit, but it pulls a little bit each time. And because they don't have sort of bleed systems as such, constantly taking air out, that's why you get some aeration in some taps. Does that help? Does William?
Yeah,
Thumbs
thanks.
up.
Thanks very much. Yeah.
Welcome.
Really clear. Thank you, Colin. I also have a question.
Go for it.
So I'm really interested in, that high level slide where you have all the various pumping technologies.
Yeah.
You mentioned one of them with applications in Victoria and England. I'm interested in sort of which technologies arised earliest and those which have arisen fairly recently. Is there sort of a way you can talk through that?
It's really difficult because if you look at what I call a diaphragm pump, you've heard of bellows, yeah? Someone opens the bellows, pulls
Yeah.
the air in, closes the. That's doing it with air, but you could do it with water. So that's a diaphragm pump. So how long has the bellows been around? Yeah. And then you look at, the piston pump, because that was just the most basic. So someone's obviously worked out, some tube thing. You're moving it and you can pull liquid in and out. But I've also seen, I will mention a water authority, has a wonderful example of a steam-driven centrifugal pump. It's not run, it's not used, but I've walked in there and seen it on a water treatment plant. Incredible thing. You and I can sit in the casing on a chair each and have a cup of tea. It's that big. And then you've got a steam engine beside it driving it. The peristaltic, one of the things I used to do when I used to teach people on peristaltic pumps, I'd buy a load of McDonald's milkshakes and I walk into the training room and I give everyone a McDonald's milkshake and get them to start sucking it out and then say, just grab your straw and put it up and do it that way. But the peristaltic pump, so which is the oldest of the pump technologies? Probably the diaphragm type approach, being realistic.
I appreciate it was a very difficult question to answer that because I think it all depends on what you define as a
It
true
does, yeah.
application of the pump, doesn't it? Ian's also flagged in the chat the Archimedes screw as well.
See, that's another one, but it's again turning. The Archimedes screw was one I was definitely thinking of. That was one of the other technologies that I didn't talk about. But I'd go
Perfect.
with I'd agree with Ian on that.
So Ian's also flagged it would be good to look into impeller technologies and different impeller types on centrifugal pumps. He's
Happy
also a
to.
pump geek, so possible sort
Oh,
of collab going forwards. Some other questions in chat. Helen, are these all pump technologies controlled by speed/stroke? And please, can you explain what speed and stroke of a pump mean?
that yes, I can, but it's different per pump technology. Because if you're talking speed of a diaphragm pump, a flappy pump, the faster you move it, the more it's going to put through. But if you move it too fast, it's not going to let the chamber fill as well. Whereas if you're talking a centrifugal pump, because you've got a rotational speed, you can run them at 2,900 RPM. You'd never run your diaphragm at 2,900 strokes per minute. So speed is used to control them, but it's very pump specific. So there is limitations all the way up and down. Does that answer the question? And the speed does have an impact on the flow. You can adjust the speed to change the flow rate.
Thanks, Colin. We have a second question from Helen as well. If you have a pump that's always getting air in the system and there are no air release valve, what is the best way to troubleshoot this?
My honest truth is I'd have to come and look at the system. Again, I get to travel around the country, so if it's not an urgent thing, I can meet on site. But yes, because one is why is the air getting into the system? And if air's getting into the system, it normally means there's a suction side issue. So when I was talking about the suction side of the product, there's something not working right there to ensure that the flooded suction isn't bringing air in. Or if the product being pumped is aerated to a certain degree, then you need to look at something to remove the air. It's one of those, there's no straightforward answer because there's so many options.
Yeah, that makes sense. Thanks, Colin. I'm just seeing if we get any other questions in the chat. I think there's definitely appetite, Colin, for a follow-up, and there will be a survey issued after this, so we can get some feedback that way too. We can take that away and look to see what a second session would focus on.
Perfect. Well, I mean, to talk about things I've pumped, everything from nuclear waste to cooling water on nuclear storage swimming pools. I can't tell you where, I can't tell you any of this. I've told you the strangest things I've pumped are things like things that go bang, but I can't say where, when, or how. But then there's certain things, foodstuffs I pumped. I was talking about mince pies, and I still love mince pies. So I'm not going to be put off that. There's other things that I've pumped that I won't eat, but mince pies is one I definitely will eat. Ice cream, again, pumps are used in the manufacturing process, but I couldn't imagine life without ice cream. But then you look at, other things like a lot of, I was talking about the body products, the hair products, the face products, everything else. It's amazing how much stuff. I mean, the strangest liquids to pump are things like custard. But when you're talking about liquids, you've got pseudoplastic, thixotropic. It suddenly it's a whole new level. But did you know you can walk on custard? And people, huh? Fill a bath with custard. If you try and walk gently, no, you're sinking it. But if you stomp hard, you'll be able to walk across it because it's sheer thickening. So the more energy you impact to it, the stronger it gets. If you don't impact enough energy, you just sink in it. And then you go liquids that go the other way. So it's incredible. And that's been my many years of enjoyment. But yeah, happy to, if guys have topics they want more on or think this one's interesting or that one's interesting, quite happy to take it to the next level for you.
Absolutely
That's me done.
fantastic. Thank you so much, Colin. And thank you everyone for the questions and for listening in. Absolutely fantastic. I think, Colin, at one point we had over